So now we're going to talk about how to find the volume of a solid if you rotate around a non-axis. And what I mean by that is you still have an axis of rotation, so there is an axis, but not an X or a Y axis. So we're not just going to rotate around X equals 0 or Y equals 0. We're going to rotate around X equals C, so some constant, and Y equals C, other than 0. So let's say that we have y equals c and we have it above my two curves, and we're going to go from A to B, and that's going to be from here to here. We're going to say that, oh, there's actually a point of intersection, so I'm just going to make that my B. All right, so I'm taking this area between my two curves, and I am going to be rotating that around just like I would with the x-axis, but now I'm rotating it around some y equals c. Oops. Try to draw my picture first. And I don't know if I do this to myself. 2.5 units away. Something like that. Okay. So what this looks like when you rotate it around, something like that, right here, I'll draw my outer, and then one of my representative rectangles, if I rotate that around, becomes a representative washer. So there's one of my washers. All right, so the volume of the solid is still going to be adding up an infinite number of infinitely thin washers. So it's going to be pi r squared minus r squared. The thickness of this washer is going to be dx. We're going from A to B. The difference is what is big R and what is little r. So big R is the distance. It's not just the function, okay? It's the distance from the center of the washer to the outer function. So that's not the function itself. The function itself, or going in the other direction, let's go actually this way to actually touch the original function. The outer radius, the bigger radius is going to be the distance from the center of the axis of rotation to the outer function. So again, that's not just the function. It's not just f of x. It's the distance between c and f of x. So if you're looking at this distance of this purple line right here, that's my larger radius. Okay. Now c is the distance to the x-axis. So this whole thing is c. And then this part right here is the distance between f of x and the x-axis. So if you're calculating the distance between the function and the axis of rotation, it's going to be the axis of rotation minus the function. Because again, c is the distance, this whole distance. F of x is the distance between the function and the x-axis. So the distance between them, you're just subtracting. Similarly, your little radius is going to be the distance from the center to the inner function. Okay, so that distance right here is going to be c minus g of x. So it's still going to be like outer function and inner function. That's what this is. So f of x is the outer function. It's the one that's furthest away from the axis in this case. Well, in all cases. And then g of x is the inner function, because this comes from finding the volume of a washer, which is like your outer cylinder minus your inner cylinder, or outer disk minus your inner disk. So what that becomes when I put all this together is it looks like this. Pi times the integral from A to B. Big R is c minus f of x squared minus little r, which is c minus g of x squared dx. So it is still the washer method, or if you had the disk, if it created a disk, it'd still be the disk method. But the big R and little r, you're gonna want to set these up separately before plugging them into your integral. Don't start with an integral on these ones. Start with big R, then little r, then plug it into the formula. Okay. So likewise, if I have y equals c, let's say c is below my two functions. So when I rotate this around y equals c, so I need to create some symmetry here. So this is, let's see, about 1.5 units away. That's 2 units away. That's 1, 2, 3, 4 units away. Okay, so that one looks like this. And then, let's see, 2.5 units away. Still about 2.5 units away. And then it crosses like right here, so that looks something like, I'm doing my best, y'all. There we go. So if I have A is here and B is here, that's going to be all of that rotated around y equals c. So it's kind of my outer piece that I'm looking at. Okay. And then if I have my representative rectangle, say here, when you rotate that around, you have a washer. The thickness of that washer is still going to be dx. So you kind of have like this bowl looking thing on the outside with kind of the vase on the inside. All right, so it's still going to be pi big R squared minus little r squared times the thickness. So I'm going to set up my big R. Now in this case, the big R is not going to be c minus f of x. And the reason for that is because c is now below my functions. In the previous example, c was above my functions. But it doesn't really change that much. The radius is still the distance from c to the outer function. But now f of x is higher than the axis of rotation. So if f of x is above the axis of rotation, then that's going to be f of x minus c. So again, very similar to what we had in the previous example. It's going to be upper minus lower. Okay, so just remember this rule. We always do upper function minus lower. And the upper function is f of x in this case. C is the lower function. That still applied to this problem where c was the upper function. It was the axis of rotation. But since f of x was below it, it was c minus f of x. Okay, so just remember when you're coming up with r, big R and little r, it's upper minus lower. Whatever is the upper function minus the lower function. And then when you're thinking about the difference between big R and little r, the only difference is that the inner function is going to be your smaller radius. The outer function is your larger radius. So we have upper and lower functions. We also have inner and outer functions. Okay, and then your volume is still pi times the integral from a to b of big R squared minus little r squared. The thickness is dx. All right, when we are rotating around x equals c, so now we're rotating around a vertical line. That's terrible, but I'm gonna just leave it. 1, 2, 3 units away. Okay, something like that. And we're going from, let's say, A to B. My area, I'm rotating it around. X equals c. my representative rectangle. Again, this is going to be washers that are stacked on top of one another. This is not going to be where they are next to each other. And because of that, the thickness is dy, not dx. The thickness of that disk is dy. Okay. All right, so I need to set up big R and little r first. So big R is the distance from the axis of rotation to the outer radius, or I'm sorry, the outer function. The outer in the function in this case was f of y. Now the question is, we normally do we normally do upper minus lower, right, to figure out big R and little r. However, with f of y, or when your thickness is dy, it's not it's not upper minus lower, it's going to be right minus left, okay? Because the quote-unquote upper is always to the right. So if you think about like your x-axis, the upper numbers are to the right, right? Like 5 is bigger than 4, which is bigger than 3. So the upper function is the one that's more to the right. So looking at this, we have our x equals c right here. We've got f of y right here. So which one is more to the right? Which one is the quote-unquote upper function? That's going to be c. Likewise with little r, which one is more to the right? That's c. Which one is more to the left? G. So c minus, g of y. I wrote f of x instead of f of y. But these functions do need to be in terms of y because your thickness is dy. And then that makes your volume pi times the integral from a to b. And remember, your bounds have to be in terms of y as well, of big R squared minus little r squared dy. Okay, and then quickly I'm going to do the same thing here. There's g of y. I'm going from A to B, rotating that area around. So there's so I have like a bowl with like a funnel cut out of it. My representative rectangle is right here. And then that becomes a representative washer with a thickness of dy. So big R and little r. Again, it's going to be upper minus lower, but since quote unquote upper is to the right in this case, that's going to be f of y. F of y is more to the right than x equals c. It's the quote unquote upper function. So it's going to be f of y minus c. And then my inner function is more to the right than c, so g of y minus c, and then pi times the integral from a to b of f of y minus c. Oops. Let's just set a parentheses here. Squared minus g of y minus c squared dy. Okay, so those are your general rules, but the big thing to remember is that your big R is your outer function, your little r is your inner function. And we always do upper minus lower. So if your axis is on top, it's going to be axis minus function. If your axis is on the bottom, then it's going to be function minus axis. And then same thing with the left or right. The function that's more to the right is going to be the what you're going to subtract from. So it's going to be the function more to the right minus the function that's more to the left. And by function, I mean one of those is going to be x equals c. All right, so let's do some examples here, and these are going to be not just necessarily washers using the axis of rotation method. This is kind of a review of problems. So if you want to, you might want to pause the video and try the problems yourself. Otherwise, I'm just going to go over all 4 of them as examples. So h of x is the parabola you see, k of x is equal to the line. We are setting up the integrals to calculate the volumes. So rotating around the x-axis. So that is going to be the washer method, because what you're going to end up with, and I'm going to do my best to draw what this is going to look like. When you rotate around the x-axis, right, it's going to look something like this, where it's like a bowl on the outside with a cone cut out of it. All right, so I'm going to use the washer method. So the volume is equal to pi times the integral from a to b. And since we're rotating around the x-axis, I know the thickness will be dx. So my coordinates that I am going to use are going to be along the x-axis as well. So I'm going to go from 0 to 3, since it's the area between them, and my first point of intersection is at x equals 0. My second point of intersection is at x equals 3. So that's from 0 to 3. And then my outer radius is the parabola, and my inner radius is the line. Actually, you know what? I'm going to write this a little bit differently. It's h squared of x minus k squared of x. I can do that instead of having to use a million parentheses, dx. And since we're just setting up the integrals, then that's fine. Obviously, I would expect that you would know how to do the algebra and solve. But since we're just setting up for this problem, that's all you need to do. And notice that I didn't actually write down what h and k were. I am allowed to just leave it as h of x and k of x because it has been established that these equations exist. So if it's already been established that you have like h and f or f and g or whatever, you can just use those. Save yourself some time and space. All right, about the line y equals -1. So y equals -1 is a horizontal line, but it's way down here. So now we're rotating around this. So it's gonna look a little similar, like we still have this area, but now we're farther away from my axis of rotation. So it's gonna look like this. So again, it's still like a bowl with like a funnel cut out of it instead of a cone. But we are still going to, if we use the washer method, we're still going to have thickness of dx. So my volume is going to be pi times the integral. Because my thickness is dx, I can still use the x coordinates of my points of intersection. So that's going to be 0 to 3. But what's going to be different is your big R and your little r. So your big R is the distance from the axis of rotation to the outer function. And it is upper function minus lower. So in this case, because f of x is above the axis of rotation, it's going, I'm sorry, I said f of x, that is h of x. H of x is above, so it's going to be h of x minus, and then we're rotating it around y equals -1, so -1 minus -1 becomes +1. And then your little r is the distance between the axis of rotation to the inner function. The inner function is the upper function. It's above the axis of rotation. So that's going to be k of x minus -1. So it ends up being +1. So that's going to be h of x plus 1 squared minus k of x plus 1 squared. Thickness is dx. Big R squared minus little r squared, and you do need to use parentheses around the h of x plus 1 and the k of x plus 1. I have used the minimum amount of parentheses that I could possibly use. All right, around the y-axis. So this one is going to be a little trickier because when I rotate around the y-axis, this area, if I rotate that around the y-axis, it's going to look like this. So what's going to be weird about this is that you're going to have to use two different integrals. And you know what, I'm actually just going to do this on the picture and then I will erase it. And 3. So the problem with this is that if you have your representative rectangle here, that's going to be from the distance between the line and the parabola. But if you're up here beyond y equals 3, that's the distance between the parabola and the parabola. And remember, we're going to have to write these in terms of y anyway, and you're not allowed to just write h of y. You do need to actually solve for what the function is in terms of y, because it has not been established what h of y is. If you're going to use a function, it has to be an established function. So either you have to establish what h of y is equal to, or they would have had, the writers of the problem would have to establish what h of y is equal to. So don't think that like, oh, I'll just write h of y. That doesn't mean anything unless you solve for what h of y actually is. So we are going to have to use two different integrals, and we are going to have to solve for h of y and k of y. So I'm going to do that first. If y is equal to x, then x is equal to y, so k of y is equal to y, so that's easy enough. And then y is equal to negative x minus 2 squared plus 4, subtract 4, divide by negative 1. Take the square root. Don't forget, when you take the square root, you have to put plus or minus, and then add 2. So h of y is 2 plus or minus root 4 minus y, but I'm not even going to write that because I know with that plus or minus that's kind of contradictory almost, like you have a positive square root and a negative square root. So you are going to have to figure out which you are using. Are you using the positive root or the negative root? Sorry about that. I'm going to finish this and then I will pause the video and finish it in a second. So the first area is going to be between 0 and 3. So I'm using 0 and 3 as the y coordinates. So I'm going from 0 to 3. So that would be pi times the integral from 0 to 3. My outer radius is going to be just y. And my inner radius is going to be, and now this is where I need to figure out if I'm using the positive or the negative square root. So this is how you figure it out. The positive side is always on the right. The negative side is going to be on the left, okay? So because for this area here, we are using the negative side of the root, that's going to be 2 minus root 4 minus y squared. dy. So, sorry, I changed colors there. That is only this area rotated around. So that's not the volume of the entire solid. So I need to add this area rotated around. And my lower bound is 3, my upper bound is 4. Again, we're in terms of dy, so your bounds need to be in terms of y. Then your outer radius is going to be the positive root, because again, it's the parabola and the parabola, which is going to be both sides of this equation. So the outer function is going to be 2 plus root 4 minus y, and the inner function is 2 minus root 4 minus y. So this entire volume, this whole thing, is what that both of those integrals is what you need to calculate the volume of this entire solid. So you have to split it up into 2 areas, which means you're going to have 2 integrals. We're actually going to learn a method that's going to make this a lot easier and will be less work, but we won't learn that method until next week. All right, I'm going to pause the video now because you guys want to come into the classroom. Okay, in the last part of this example, we are rotating around x equals -1, which is right here. So we are not rotating around the y-axis, we are rotating around a vertical line. And I am going to have to use the washer method again. My function, when I rotate it around, will look something like this. Just going to do a quick sketch. So very similar to the previous example, but further away from our axis of rotation. And we're going to have the same problem that we had last time, which is that you have two different areas. You have the area from 0 to 3. When you rotate that area around, that's the area between a line and the parabola. And then when you rotate the other area around, that's the area between the parabola and the parabola. So you need 2 square roots. So your first volume integral will be pi times the integral from, we're still going to have y bounds of 0 to 3. Your big R, actually I should write these out separately, r sub 1 and r sub 2. Your outer radius is going to be the distance between the axis of rotation and the line, which is going to be upper minus lower. Again, upper is more to the right, so that's going to be, not x minus, but y minus -1. And then your inner radius is going to be the distance between your parabola, which is going to be the negative side of the square root, and x equals -1. So that's going to be 2 minus root 4 minus y minus -1. So that is for this first area here between the line and the parabola. So that's going to be y plus 1 squared minus 2 minus, and you can combine the 2 and the 1, I'm just not doing it right now, plus 1 squared dy. So that's going to be your first volume. You need to add it to your second volume. Again, my bounds are between 3 and 4 because we're in the y direction. And I'm going to say r sub 2 and little r sub 2. Your outer radius is going to be the distance between the axis of rotation and the positive side of your square root. So that's going to be the quote-unquote upper function, the one that's more to the right, is 2 plus root 4 minus y. And we are subtracting -1. And then your inner radius is going to be the negative side of the parabola, or the negative side of your square root, minus the axis of rotation, so 2 minus root 4 minus y, -1. And plug those into r squared minus r squared, 2 plus root 4. Again, you could have combined the 2 and the 1. I don't know why I'm not doing that. Doesn't really matter either way. 2 minus root 4 minus y minus 1 squared. And don't forget your dy at the end. So again, this whole thing is the volume of the solid, but we will work on a shell method next week, and then that will actually simplify these equations quite a bit. But you should know both methods, because the shell method is not on the AP test. These methods are on the AP test. So you do have to know both.